Obrigada. Before I start, is there anybody here that wants to talk in English? Are you all Portuguese? Then, all right. So, thank you for the introduction. My name is Filipa, Peleja, and the objective of my talk today is to let you know a bit about what's going on nowadays regarding NLP. So, natural language processing algorithms is not something not new, so they've been going on for quite some time. But why there's so much attention to it? So, what happened in the past few years? What happened is that deep learning came up. And deep learning also, if you think about neural networks, nothing new, but the algorithms, the capability for us to be able to build models that can answer the needs of something that we didn't do in the past, this is the different thing. And it captured attention, not only industry, but also academics. So we have these both worlds booming on trying to improve more and more what we have nowadays. And the other interesting thing is, and even here in this conference that we see Microsoft and other players, they have a lot of products that behind the curtains, what you have is NLP algorithms doing their work. And I'm giving you here a couple of examples. You can think about Alexa, Siri. So there are a couple of algorithms that what they do is they try to do this question answering, problem solving. And they become so good and in real-time capabilities that right now, most of us have at least one of these devices in our homes. But it went a lot beyond that. So I'm talking here about this Hello World. It's actually, I'm not sure if I'm going to spell it right, Chiance. It's a Microsoft product. But what is this? What is the difference between this product and Alexa? The difference is that we are talking about an artificial intelligent system that aims to be your friend. And this is actually growing a lot. So we're talking about people feeling emotions toward a device that is not human and is getting back to us and building a relation. And, well, these are just some examples, and this is something that in the past we weren't able to do it as good. Okay, this is why it's been growing a lot. And before I move forward, another thing that I want to call out for attention is the impact of NLP in healthcare as well. Because we can see that nowadays we are able to look at all the records that we have from our patients' health, and we are able to help the doctors and so on in doing their work. And this is something that we are able to do it using NLP, deep learning. All right, so why this boom and why is it going on right now? So it's not much longer than 5 years ago, and it began with sequence-to-sequence. And the basis for that was the word-to-vec algorithms, and behind what we have is the capability for us to look at a piece of text, take all the tokens, it can be a word-based, and we build a vector. So it's called the embeddings, but what is actually giving us, what is different from what we had before? The difference is that these vectors project, let's say, our words, our tokens in a given space that gives us information about their semantic relation to other words. All right? So this is one of the biggest advancements, and having that, let's say, basis, we had all these algorithms coming up. So we had the sequence-to-sequence, which was introduced by Google, and then we had all the different models. Attention models, for instance, are the ones that use transformers to it, and we are able also to take a closer attention to the word itself while we're doing the encoding, and not only looking only for the full sequence, all right? And the other thing that I want to call out attention for is, well, we have this big community, I told you, industry and academics, so it's not focusing on one single world, let's put it that way. And the idea behind is, why not we kind of push this for us to bring more people to use it? Because if you increase the community, what happens is that you have more advances to it, right? So PyTorch and TensorFlow, they were introduced in 2017, so they don't have much more than 3 years, and now they are widely used. And what did this allow us to do? It allows us to use these algorithms for different problems without having to build these algorithms from scratch. And this is quite important because these algorithms are quite complex, and if you always need to build it from scratch, you might not have the time or the know-how to do it. And this type of, let's say, frameworks can help us achieve that. And finally, the last point is, well, behind the curtains, what deep learning allowed us to do was for us to answer problems that in the past we couldn't. And one of the major reasons for that is that we needed a lot of annotated data. This annotated data is quite expensive, so we weren't able to scale up. And deep learning allowed us to work with unlabeled data. Okay, but at the same time, it doesn't mean that they can't improve using labeled data. And if you have more and more people using it, the consequence for that is that all of a sudden, we have a lot of large-scale data sets made available for us to improve our models. And this is quite a positive thing, which leads us back again to the frameworks, right? Why we want more people to use it? Well, we are gaining through it, right? Because we are also gaining all this, for instance, question-answering data sets. All right. And one valid question could be, well, but NLP has been going on for quite some time. Should now I only use deep learning for NLP? And my view on this is no. Depends on your problem. So you don't need to use deep learning for everything you got. It's like using a canyon to resolve a very simple problem, right? And this plot, what I want to show is that we should go for deep learning approaches if you have one of these situations. You have a really large data set. It's too big. You don't have annotated data. And it means that you need to scale it up. Then deep learning might be the answer for your problem. All right? And then again, the complexity of the model. Even if you have enough data, but your model needs to be tuned and so on, so to answer your needs. So you need a more complex model, then you go for deep learning approaches. And this is what you see here, right? So you can see that what happens with traditional approaches is that they're quite good, but then they kind of converge, and they struggle a lot to improve their performance. Here you can see accuracy, but you can think about different performance metrics. All right? So these are kind of a sum up of the challenges that we have. So we want translations, and now I'm going to focus a bit on machine translation, and we want them with quality. And this, like I said before, it demands a lot of human expertise, which is expensive, and many times it's not feasible. And you can think about popular data sets that are used for these problems. I'm showing you here a couple of them: the European Parliament, TED Talks, Wikipedia. What we have here, we have the parallel documents. A parallel document is when I have the same text written in different languages. So it can help the model to be able to learn which is the translation, all right? But the limitation here is that, well, we are limited to the domain. All right, and also the size of this data, okay? So this was one of the biggest challenges, and this is why deep learning came up and helped us, boost on this. And where we have a lot of data, and we will also want to learn from it, it's from popular websites, for instance, from Twitter and so on. So what is the characteristic here? Well, yes, I do have a lot of textual data, but it's in one single language. Right? But I want to be able to translate it, and how can I learn from it? All right? So these were the challenges. And what deep learning came up to is that, well, what I'm going to do is I'm going to use unlabeled data, and I'm going to learn from it, okay? And what I'm going to do is I'm going to build these language models by looking at a collection of text written in one single language, all right? So I can have a lot of different models. And the word embeddings that I was telling you about, that was the idea behind. And you can have here, I'm not focusing on one specific model, all right? So I'm going to tell you a bit about the characteristics of different ones. So you have the context-free and the contextual. And the difference is I can build a vector, for instance, a word embedding vector, and it projects a given word in this space, but it's context-free. So what does this mean? It means that, for instance, if you think about the word bank in terms of institution, and you think about the bank from a river bank, both words are written exactly in the same way, but they are used in different contexts, right? And this is one of the challenges. So what you have is, if this is important for you for your model, then you should use a contextual-based deep learning algorithm. And this is what's going to do is that it's going to give you more than one representation for that word, given its context, all right? On this second plot, what I want to show is that what happens if we use these pre-trained models. So we use deep learning to build these models, and if you don't use nothing at all. So if you're not using nothing at all, you're going back to the traditional algorithms, and you need the label data. So you can see in the blue line is those algorithms. In the axis, what you see is while we have more and more label data, and we can see the dependency of the quality of these models based on that. What happens with the red line? So this is the ones that we had deep learning, right? And this is why it was such a huge impact. Right from the start, with a very low amount of the label data, the model, it outperformed the traditional models for quite a lot. So you're seeing here the blue metric. All right? The blue metric, basically what it's doing is looking at how many, let's say a translation I have, words that were correctly translated, and takes into account also the sequence. Okay. But then you can say, well, but this is not enough, right? I want to take more advantage of the data that I have available. So what can you do? You can do the self-learning. So what is the idea behind? I have a lot of unlabeled data, right? And I'm going to use the labeled one. I'm going to build my model. And then I'm going to use that model to predict over the ones that I didn't know. And I use those, let's say, as ground truth. So I use all of that together, okay? Advantage, I can use more data. Disadvantage, it's what you're looking at in here, right? You're going to have a lot of bad translations. For instance, you can see the translation that comes, it's saying that I traveled to Belgium, and then it says, je suis étudiant, in a translation from English to French. So this is a problem, okay? But I am gaining something at the same time, right? So it's a kind of, let's say, a good trade-off. If, again, I need a lot of data. If my model was good enough with a small amount of data, then I didn't go for this approach. You see? So I also want to call attention for this, because many times you want to go for the more robust models, but it depends also on your problem. Okay? All right. And as I was telling you, so we have these bad pairs, right? Because I was using unlabeled data. So how can I overcome this problem? So we can use the back translation technique. What is the logic? I will learn from one direction to the other. In the direction is I'm going, for instance, from English to French, and then I'll do the inverse translation from French to English. And this actually allows us to kind of see this bad translation only as bad inputs, and you can see this as the importance of that particular pair, it decreased. So that's what we're doing in the training phase, all right? Okay, so in terms of performance, I'm telling you all this difference. So you could see this as the evolution of the algorithms that were coming up, because we had the first one, and then people, all the different communities were working on building more and better models. We have here the transformers. So it's one of the deep learning algorithms that what the idea behind is using convolutional neural networks together with attention models, those that looked actually to one single unity instead of looking at the entire sentence. And basically what I want to show you is see the improvement of the blue metric if we use the transformer algorithm together with back translation. So it's worthwhile for us to do this if we are actually doing self-training, all right? Okay, so now let's look at this space. I really like this plot because many times when you're trying to understand how these algorithms work, and it becomes a bit abstract when I'm talking about these word vectors, right? And I'm talking about this space. So this is what we have. So in different colors here, what you have is words from different languages. And now let's focus on the blue color. So in blue, I have the English. And I built my word embeddings, and I projected in this space. What's the rationale behind? For instance, if you look here in the middle, you have on the top party and group. So these two words are projected in this space, and they are very close to each other. So this is one of the really precious things about word embeddings, because we can see that they are close semantically to each other, even though the words, they are family, it's not near. So what happened? Using the collection of documents, he was able to build this space and know that they are semantically related to each other. So that's what it was able to do. Now, going back to machine translation, what we want to do here? Well, what we want to do is, why not use this characteristics, this structure of the word embeddings, for us to be able to improve our machine translation models? Okay, so I'm going to build, again, this space, and I'm going to project my other language there. And this is why you're seeing now in pink the other language. And what do I want to do? Well, the assumption is, what if I can do a mapping between these two spaces? And supposedly, the idea is my words pair, translation pair, should be together when I do this overlap with the different spaces. So the rationale is, I want to keep the structure. Visually, what I was explaining you now, what is going on is something like this. So here in the X, what you have is the space for one given language, all right? And you can see here you have cat, feline, car, deep, and I build this space. This means that I build a model for this language, all right? And I projected in this case, my units are the words. And then I have the other space, which is for the other language, and I did exactly the same. But they are disjoint, right? So the word translation that I want to do is, let's put it together. The strategy behind is, let's try to find out which matrix W allow us to do that. So you can think about a certain special factor to it. And in the end, this is what I want. In the second image, what you're seeing is the overlap between the two spaces. And I can see that the word cat and gato should be the translation of one another. All right? And again, this is done fully unsupervised, which is super good, because you can take advantage of a lot of data that in the past was very hard to use. Okay? So far I've been telling you really nice things, but it's not perfect, and there are certain limitations to it. So in this plot, what I'm showing you is, in the horizontal lines, you have the fully unsupervised strategy, all right? Which was a bit of what I was just explaining to you. And then in the other lines, what you're seeing is algorithms that are using a deep learning approach together with some parallel documents, so translations of one another. We can't see that then, again, if you have a smaller amount of data, it is worthwhile for us to do this type of approaches, because clearly the blue metric is much better. But as it increases the number of training examples, the model improves its quality. All right? But keep in mind that we are here looking at the performance with deep learning. All right? What is the difference? Fully unsupervised or not? All right? What is the limitation? Well, this is really nice. If you have languages that kind of share a similar structure to it. So that overlap of the embeddings I was telling you about, it works very well in that reality. But if you do want to make translations with words, with languages that have a different structure to it, then this will not work. And actually, it will not work at all. If you look here on this table, what I'm showing you is, if you have a supervised, so it's some parallel documents to it, the blue is more or less 20, but if you go then for this unsupervised strategy, we have like 1.5, 4.5. It does not work at all. So this is nice, but then we are really limited on which languages you want to translate from one to another. We need more, all right? So this is why last year came BERT. So maybe some of you heard about it. It became really popular, and now actually you have even more on the top of this approach. But basically, this was the first unsupervised bidirectional. So bidirectional, what does it mean? It means that when I'm looking at a word, I'm looking at what happens before that word and after that word. So I'm having the full context before and the after. All right? So you can think about this here. It's like an encoding that I have for the different units. All right? And I do this considering what I said before and after, because this will have an impact on what I want to predict as my translator, and also what is the word coming after a word that I have typed. All right. So BERT not only allowed us to be able to translate to languages that are structurally different, but also allows us to see that we have right now, using an unsupervised approach, a much better performance, that it's very, very close to the supervised one. So keep in mind that the supervised ones, state-of-the-art, are the ones that are labeled. And all of a sudden, here you have, in the first column, English to French, then English to German, and English to Romanian, all right? And we can see that the performance is really good. And regarding the English to Romanian, which are the ones that are quite different, we can see that the unsupervised model. It even improved over the state-of-the-art, which had the label data. So BERT is super powerful. Something that I didn't mention so far, when I'm talking about these models, what's going on is that they are pre-trained. Okay, it goes back to one of the initial slides. So what does this mean? To build these models, you require a really large amount of documents. So it's not something that I could do, for instance, in this machine, because it demands a lot of computing power. But what is going on is that they are built in, let's say, big servers, and they are shared for the community. So it means that when I start to resolve my problem, that is given to me, my challenge, I will not start from scratch. I will have a pre-built model, and now I'm going to do a fit to my specific problem. So this is what's going on here. Okay? And the last thing I want to tell you about BERT, and this is why it was such a huge boom, is that, well, you're seeing again performance metric, bag of vectors, you're talking about the word vectors, word2vec, and then you have neural networks such as LSTM, long short-term memory, and also GPT is something similar to BERT, so it's also a big transformer using a large amount of documents to it. But all of a sudden you have something that we did not have before. We have a performance that is super close to the human annotator. And this is a stepping stone in the NLP. All right? So this is really super exciting times. All right? And having that said, and seeing the power of BERT, what we can see here is in the plot, in the axis, what you see is the year. And by the end of this, we see 2019. And because BERT was so powerful, all of a sudden, we saw a lot of players, such as Google, Facebook, Microsoft, coming up with their models and making them available for the community, for us to use it. So the idea is let's build on top of this and get even better models. All right? So what's next? Right now, what we see is that there's a lot of effort on scaling up and providing even more larger pre-trained models for the community. And a final note is the social impact. So I started by saying that this is all over the place, right? So we have, I would say, all of us have at least one of these devices with us. But then this actually raises a lot of concerns in terms of how well they do, because they are impacting our life. All right? So in terms of fairness and discrimination, it's very important to take that into account. Just take out one example. About 1 or 2 months ago, we had the scandal from Apple where they discriminated to offer one credit based on gender, for example. So this type of things you need to be careful about. And we are looking at text, because you're looking at all the data that we have from that person to make this type of decisions. All right, so I do not have here code to give you, but I do have it available. So if you want to see how easy it is to implement these learning models for translation, drop me an email and I'll send it to you, all right? The idea is also to show you what I was just telling you, that this is made available for the community, for us to be able to start quickly and do not think that this is like, let's say, in Portuguese we say bicho-papão, right? Like it's super scary. No, we can work on that because right now we have really nice frameworks that allows us to put this in place. Thank you.